Hello and welcome to Automotive Radar, from first efforts to future systems. My name is Sean Gang, your host for this IEEE MTT Society webcast. Before we start, I will mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We will send all registrants an email when the archived webinar goes up, so you can revisit it or share it with your colleagues. Second, we encourage questions. We will answer them after the talk, but you can submit them at any time during the discussion. Enter your question in the Q&A box in the webcast window, and do not forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the rectangle at the top right of the live slide window. You can also enter full screen mode if you desire. Refresh or reload the current web page if you encounter problems. With regards to audio, if you're listening over the computer speakers, you can adjust the medium player volume. You may also need to adjust your system's master volume. The icons at the bottom of the webinar window include a resource list. Clicking that link will start the process to download copies of the slides to be presented today. Now, let's introduce our speaker. So today, Professor Christian Waldschmidt is our speaker today, and he received the master and the doctor degrees from University of Karlsruhe in Germany in 2001 and 2004 respectively. Since 2004, he has been with Robert Bosch GmbH, and he was heading different research and development teams in microwave engineering, RF sensing, and automotive radar. In 2013, he returned to academia. He was appointed as a director of the Institute of Microwave Engineering at the University of U.Ulm, Germany, as full professor. The research topics focus on radar and RF sensing, millimeter wave and sub-millimeter wave engineering, antennas and antenna arrays, RF and array signal processing. He authored or co-authored over 270 scientific publications and more than 20 patents. He is chair of the IEEE MTT 29 Technical Committee on Microwave Aerospace Systems and served as chair of MTT 27 Technical Committee on wireless-enabled automotive and vehicle applications. Since 2018, Christian Waldschmidt serves as an associate editor for IEEE MTT Microwave Wireless Component Letters, MWCL. Now, it's my pleasure to turn the virtual podium over to Dr. Waldschmidt for his talk, Automotive Radar from First Efforts to Future Systems. Please.
Okay, so welcome everybody to my webinar here on Automotive Radar. And thank you, Sean, for this very nice introduction. I would like to talk about automotive radar and look back into what has happened in the past. And then we look into the future. And of course, we spend most of the time to look on the research trends and see what comes in the future. Here is a short agenda. So we will look back on how everything started from the very first trials in 1959. And then we look briefly onto the state of the art. I will show one of the radars that is produced today and used on the streets today. And then we spent most of the time to look on the future systems. And there's one key question that I would like to address, and that's the question, what could a future radar configuration for highly automated driving look like? And we dig deeper then into three different topics. One of them is high-performance radar, and we look into digital modulation schemes for automotive radars. And then we leave the single sensor and look at configurations of complete systems of sensors. So we look at radar networks, and they can be used for grid mapping and synthetic aperture radar. And that are the topics I would like to address. Of course, there are many more topics in the field of automotive radar that we could present here, but we are limited in time, so we will focus on those topics. So let us first of all go back like more than 60 years. In 1959, as much as I know, everything started with Cadillac, GM, and they integrated two, well, really large radars into a vehicle. And it was basically a proximity sensing system. So they had an audible signal and a warning light for the driver. This is something we would call today a forward collision warning. And we have this today implemented in many vehicles, but actually it goes back to more than 60 years. Then in the 70s, the frequencies went up. We had the first blind spot detection system by Dunlop. And in 1974, in Germany at IG Telefunken, the first millimeter wave radar at 35 gigahertz was implemented. It was a front radar. It was bistatic setup, and you can actually see it here, how it is integrated into the vehicle. So here you see the transmitter, and this could be the receiver or vice versa. So it's a bistatic configuration. The beam width is 2.5 degrees, so it has a pencil beam-like pattern. And I brought this antenna to you, and I thought, okay, I can show it here directly like this. And I can tell you, okay, this is really heavy. You know, this is aluminum, but this is a single channel. And so it's the transmitter and the receiver. And for comparison, okay, it's really heavy. This is what the size of today's automotive radar with a large number of channels, like 60 or 90 channels. Okay, good. So that were the first pioneers in this field, at least some milestones. And let's look at the serial products that came up. The first ones in 1996, so 25 years ago, a 24 gigahertz system was implemented by Vorrat in the Greyhound buses. And it was still quite large and bulky. It had a weight of more than 3 kilograms and a range of 110 meters. And the interesting thing about this is it was actually stopped by the drivers' union because the drivers felt controlled by this system. This sounds somehow a bit weird when we think about that we have such systems today actually in every car. But this is what happened in 1996. And interestingly, at this time, it was the first time possible to really show that the number of accidents could be reduced by this system. So there's statistics available which clearly show this automotive radar or this bus radar helped to reduce the number of accidents. In 1998, Daimler-Benz implemented then the first radar at 76 gigahertz. You can see there the radar. It was actually implemented in an S-Class. In the picture, we see the E-Class. This must have been some type of test vehicle. And from then on, things went really quickly. So in the very same year, other companies came also with 76 gigahertz radars. Now, what do we have today? First of all, within the last 12 years, radar developed to be a huge success story. In 2010, we had like $200 million turnover, and this market grew to 8 billion this year. So we have a growth of a factor of 40, which is really amazing and really a success story. And today we have a well-established market for radar sensors for driver assistance systems. We have a lot of well-established tier ones. And each year there are more and more startups coming, and they address more the high performance radars. So not the standard, very cheap radars, but there's continuously new companies coming up and presenting radars. And I've brought for you here just one example to show what a typical automotive radar looks like today. So we very often have patch antennas or dipole antennas, step antennas, something like this on a PCB. So we have PCB antennas. Waveguides antennas are just coming. State of the art is rather PCB antennas. We have MIMO systems, but a low number of transmitters and receivers. Typically, state-of-the-art MMIC has like 3 transmitters, 4 receivers. 4 times 4 is coming now. We have a coexistence of CMOS and CG, but I guess CMOS will make the race. And the chirp sequence modulation is actually used today by almost all radar tier 1s. We have an angle estimation, not only in azimuth, but also in the elevation plane, which is important. If there's an object on the street, we have to decide whether we can undergo or overgo the object. So it's important to know this. Chirp sequence modulation basically means we use a very fast FMCW radar. Most radars work, or all radars work in the bandwidth from 76 to 77 gigahertz. So actually the frequency range above it would be allowed to use. And typical chirp durations are in the range of several 10 microseconds. And we use many of the chirps. So we do a first FFT per chirp to get the range information, and then we do a second FFT over all the different chirps to get the Doppler information. So the Doppler is basically sampled by the large number of chirps we use. And due to the high number of vehicles on the streets today with radar sensors, and most vehicles have many radar sensors, we have a severe interference topic. So the radar sensors interfere with one another, and that typically means that the noise floor is increased, so the detection probability is dramatically reduced. And today there are many methods available how to compensate the interference, how to mitigate the interference. Most of them work in time domain, and they're very simple approaches like just nulling or smoothing the signal, but there are also very complex methods with which you can reconstruct the non-interfered signal. We have some methods in the frequency domain, but since the spectrum is very limited and each sensor needs a large bandwidth, those methods are typically not that effective. And of course, we have beamforming. Null steering is a very powerful method because it is one of the very few methods that is independent of the modulation scheme. So it works for any modulation scheme. And this is why I think it's a very powerful method. Okay, with that, I would like to look into the future systems and to tell you a little bit what is coming. And as I said before, there is one key question. That is the question, how could a future radar configuration in a vehicle look like? And we see a split in the market. So we will have those very simple sensors for driver assistance systems, but we have more sophisticated configurations, sensor configurations, and single sensors when we think about highly autonomous or highly automated and autonomous driving. And this is what we will look at now. Good. So what requirements do we have for a future radar system that we need for highly automated driving? First of all, we want to have a coverage of 360 degrees around the vehicle. So we have like a cocoon around the vehicle, a protective sphere around the vehicle to protect the vehicle. Into the front direction, we have ranges of more than 300 meters that we want to monitor. And of course, we want to have high angular resolution in azimuth and elevation as high as possible. That is the weak point of radar. So many people work on how do we get higher angular resolutions. And there's another topic, we need large unambiguous ranges. So typically in all measurement dimensions, so in the range, in the Doppler, and in the angular dimension, we want to have very low side lobes, so ambiguity-free measurements. And of course, those radars needs to be small and simple to be integrated into a vehicle. And well, of course, we could now place, as you see it here on the top right side, many sensors in a vehicle. But by the way, today upper class vehicle has up to 8 sensors. But maybe a more practical approach would be to have one very powerful radar looking to the front, and having a network around the vehicle, maybe consisting out of 4 sensors at the corners, at the edges of the vehicle, having a very wide field of view. And that can be very simple radar sensors as the ones we use today for the driver assistance systems. So in the following, I would like now to look into this configuration and talk first of all about the sensor here looking to the front, which is really a powerful high performance sensor. And today, when you look what is driving around on the streets, the most powerful sensors maybe have channel counts like 192 channels. And we thought about, okay, let's multiply this by a factor of something like 10 or 9. And this is a sensor we have built just to see, okay, what does such a sensor deliver? What information does such a sensor deliver to us? And here you can see a picture of our high performance radar. So we have here the number of 1,728 virtual channels. So the size of this housing, so from this side here to this side here, it's something like 25 centimeters. You can see in the center the antenna system, and it's a single PCB here carrying the circuitry. And on one side, we have the antenna. On the back side, we have the MMICs. So this here is the back side, and here you see the single MMICs. So we have 12 MMICs. Each has 3 transmitters and 4 receivers. And then here we go to another board where we have the digital circuitry, the FPGA, and so on. And here we have the power supply, just power supply, and so on. And here we have some connectors. Good. Let's look to some more details. So we have 12 MMICs. There's one master MMIC, which is this one here, and the LO local oscillator signal of this is fed into this MMIC here. And from here, we go into this direction and into this direction. So these those two are more or less in parallel. So we have a distribution network of the local oscillator. And now always 2 MMICs are used together to make one transmit antenna group. So this one here and this one here, they operate together, and they have those 6 transmit antennas. And with these 6 transmit antennas, we do beamforming. So here, on the bottom left, you can see the layout. We have 12 MMICs. Each antenna, like this one here, it consists out of 4 patch antennas with parasitic patches, because we have a bandwidth of 5 gigahertz. So we need parasitic patches to increase the bandwidth of the single radiating elements. And here you can see 6 transmit antennas groups. This is one of the transmit antenna groups, and there are 6 other ones. And the receive antennas are just distributed in such a way that we optimize the side lobe level. The ambiguity function is optimized by genetic optimization. The number of channels is that high, so we do a genetic optimization. And on the bottom right side, you see a cut through the PCB. So we have the radar MMICs on one side. In green, we have the FR4 layers, and this here is a coaxial structure with which we tunnel from one side of the PCB to the other side, where we have then in blue here the microwave layers, the RF layers. And there we have a patcher-coupled patch antennas. As I said before, we need parasitic patches and patcher coupling to get the large bandwidth of 5 gigahertz for this radar. Well, what does this radar see? Here we have some measurements. Typically, when we do the very first measurements, we take a huge corner reflector in our anechoic chamber and set the radar up. But in this case, we have used just a metallic sphere with an RCS of minus 13 dB square meters. And here is what the radar sees. So we see this little target here, and we have some side lobes at minus 16 dB. And on the right side, you can see an image of our chamber. And actually, we were pretty surprised to get such an image here, because we have never seen something like this before. And this is just a single snapshot. So it's not some sophisticated imaging technique or nothing. It's just a single snapshot. here's the target, and that is the target. And in our anechoic chamber, there's here in this area a cover, because there's a hole in the chamber, and even this cover can be seen here very clearly in the radar image. And here you can count on this side and this side the single absorber we have in this chamber. So really an amazing picture we got. A special feature could be transmit beamforming. We were pretty surprised how powerful transmit beamforming is when we have seen that in measurements. Let me show that to you. First of all, here we have the patterns. So this here on the left side, it's the azimuth pattern. In the center here, we have the elevation pattern. If we take a single antenna group, so this one here, this will be a single antenna group. Now, if we do beamforming in the azimuth plane, so we take these two antenna groups together here, then of course in the azimuth we gain here like 6 dB because we have a high transmit power and we have the array gain. In the elevation plane, nothing happens. If we do the same in the elevation plane, so we take these two groups together here, and this one here, oh, it doesn't draw here, okay, like this. Then of course in the azimuth plane nothing happens, but in the elevation plane we get a focusing. And of course you can do beam steering. So here's an example. Now we have a beam, one example where we steered to 10 degrees and one where we steered a null to minus 20 degrees. Good, let me show you an application example. In this scenario here, we have a person standing here and a car standing here, and they don't move. Everything is stationary, so there is no Doppler information at all. And they are at the same range cell. So we can only discriminate those two targets by the angular information. Now, if you run our sensor without beamforming, then you can hardly see the pedestrian because it's covered by the side lobes of the target of the car. The car has a very strong reflection with the side lobes, and it covers the person. But if you steer a null onto the vehicle, onto the car, and eliminate this very strong target with a huge RCS, you can clearly see the pedestrian here standing there. So by steering a null through the field of view, you can increase, of course, the detection performance dramatically, as we have seen it here. Good. So much on high performance radars. I think we will in the future see more of those radars because they will be used for the front direction when we think about highly automated driving. Let me continue talking about the single sensor, and I think there's another development coming, and that is that the automotive radars get digital. On the left side here on this slide, I've written down the benefits of digital radars when we talk about automotive radar. But of course, there are pros and cons. So on the right side, we have the challenges. What are the benefits of a digital radar? Well, first of all, it is extremely flexible. The signal design can be changed arbitrarily depending on the situation. You can use arbitrary waveforms, adaptive waveforms. You can adapt to the situation you are in. And you can do completely new and different modes of operation. For example, implementing something like a passive, like a passive radar is very simple if you have a digital radar hardware available. Today in automotive radar, typically chirp sequence modulation is used. So TDM MIMO is used with a low unambiguous Doppler frequency. And when you have a digital radar, MIMO operation is much more flexible and much more powerful. When you have a digital radar, you can do very good radar network operation. It's much more simple to establish a network with a coherent network with a digital hardware. And of course, as I will show later to you, when we build such radars, we use hardware that was not made for radar purposes. This was actually made for 5G and 6G communications applications, but we can use this for radar as well. And there will be a huge benefit by using this, the electronics coming for 6G. Also, when it comes to interference, mitigation of interference with a digital radar is much more simple compared to an analog radar. Of course, digital radars are interfered the same way as analog radars are. There is no difference, but the mitigation is more simple when we have a digital radar. What is the disadvantage of digital radars? Of course, when we think about automotive radar, we want to have high resolution. So 1 gigahertz is nice. In the future, we maybe want to have even more. And that means we need a large bandwidth. And that, as we need to sample the whole RF bandwidth, we need really high sampling rates, a few gigasamples per second. This costs a lot, and automotive radars are very cheap. So there's still a long way to bring the prices down for this hardware to make digital radars cheaper. On the other side, there are many approaches how the bandwidth can be reduced dramatically with a digital radar in such a way that we have the high resolution coming from a large bandwidth at the RF band, but we have a low bandwidth at the ADC. Today we have two main representatives. One is OFDM, the other one is PMCW. That are two different modulation schemes for digital radars. There are some others in discussions. Just to give you an idea what such a modulation scheme look like, a short sketch on how OFDM actually works when you do this with a radar. So we have here the transmitter, the subcarrier is the frequency axis, the symbol axis is the time axis, and we have digital signals here, digital symbols. And the nice thing, or the tricky thing, is the spacing between the subcarriers. It's 1 over the symbol duration, and this leads to the orthogonality, where the name comes from orthogonal frequency division multiplexing. Then we do an IDFT to get the time signal here. You add a cyclic prefix. This is just done to make sure that on the receive side, the whole symbol is received. You serialize this and you transmit it at 77 gigahertz. You receive it and you do everything again backwards. So you deserialize it, you get rid of the cyclic prefix, you do a DFT, and you end up with your digital symbols again. And now by comparing the receive symbols here with the transmit symbols, we get actually the channel information. So we divide those symbols here by those symbols here. And when we do this, we get the channel information, which is this here. And then we do different Fourier transformations, one in the time direction, to get the Doppler, and one into the frequency direction to get the range information. And this is how we get the target information with this type of radar. As I said before, the challenge about the digital radars is that we have this large RF bandwidth of 1 gigahertz or even more that we have to AD convert. And that results in a huge amount of data and high cost for the ADC. And there are methods today how to get rid of this high bandwidth. One of them is, for example, stepped OFDM. The other one would be sparse OFDM. Stepped OFDM means here on the frequency axis in the baseband, we have a very limited bandwidth. And then we increase the bandwidth by having a very agile local oscillator. So this local oscillator here is doing something like a sawtooth function. So it does frequency steps. And by doing this, we spread our signal and we distribute our RF signal at 77 gigahertz that it looks like this here in the channel. On the receive side, we mix it down with the same LO pattern. And this is how we get then the narrow bandwidth at the digital analog digital converter. And then by some signal processing, we can reconstruct what this signal here was looking like. And with this, we get the same RF bandwidth back and get the high resolution from the RF bandwidth. And a similar approach is the sparse OFDM, where you just randomly distribute your signal in the frequency time matrix, and then you reconstruct it by compressed sensing. So there are methods today available with which you can reduce the bandwidth at the ADC dramatically, though keeping the large bandwidth at the high frequency. Here's an example of a system we built. It's like 5 years old or something like that. It's when the first Xilinx RF SoCs came up. And this is the evaluation board. Here you see the waveguide antenna in this area here. This is the board we have used. You can realize 4x4 MIMO system, depending whether you need IQ or not. We have real-time implementations of OFDM and PMCV running on this system with measurement rates of roughly 100 Hertz with a bandwidth of 1 gigahertz. So this would be parameters typical for an automotive radar. And today, this whole thing doesn't look as bulky as it's here on this image anymore. Today, of course, we have integrated this into a little housing, so it runs quite nicely. Here's one of the first measurements we did. I hope you can now see this little video. Where is the video? So there's a person walking around in our anechoic chamber. Oh, it goes very slowly. The anechoic chamber, and here's the range. On the left side, you see the range Doppler matrix, and in the center, you see the CFAR angular evaluation. So with that, I would like to leave the single sensors.
Sorry for the interruption. So for the audience, if you please don't forget to open the media player window to watch the video, which was just played. Just a reminder.
Okay, yeah, that would be good. We have some more videos. With that, I would like to leave the single sensor and focus on networks of radar sensors. So now we use many radar sensors together. As I said before, it can be very simple radar sensors, 3 transmitters, 4 receivers, not more. But now we try to capture really 360 degrees around the vehicle. And yes, if you look into the literature, there are many people working on those automotive radar networks, and they're very different approaches, and you can classify those networks in many different ways. And to keep it simple, I did here the following. I said, okay, we have coherent networks and we have incoherent networks. So incoherent means the single sensors operate completely independent, whereas for coherent networks, we somehow establish a phase relationship between the different sensors. It can be by signal processing, which is the more interesting way, or it could also be by cable, but in an automotive environment, you don't want to use a cable. A coherent network where we have a phase relation between the different sensors, so the nodes in the network, we can do coherent angle estimation, which would be excellent to get high resolution. So this would lead to very large apertures if you span, if you have the sensors far away from one another, but they're very sparse. And due to this extreme sparsity, I personally doubt that the apertures will be really span the whole vehicle. They will be smaller, like a few 10 centimeters. But still, this would allow excellent angular performance. This is why I call this a high-performance network. On the other side, if you have an incoherent network, it's extremely simple to integrate this into the car. There's no synchronization between the different sensors. It's just a rough time synchronization to make sure the different sensors do not interfere with one another, but that's basically all. And of course, this does not allow for a coherent angle estimation. So that will be the simple network approach. And what I would like to do now, I would like to focus on this simple approach. Due to its simplicity, it's so attractive, because even with this approach, you can get very nice images of the environment, and that is what I would like to show you. There's one key step before we do imaging. and that is we need to very precisely know where the radar is at a given point of time because the vehicle is moving when we do the measurement. Because what we do is we integrate up many measurements to get a nice image. And there are different techniques how to get those images. Grid mapping is something I would like to show to you. Grid mapping is more state of the art. That is what we can do today with a resolution of maybe 20 centimeters, 15 centimeters, 30 centimeters. If you want to do better, you can do synthetic aperture radar, which would mean we establish a coherent aperture when the vehicle is moving over a long distance. And that is similar to what a satellite radar does. And we can also do this with an automotive radar. But key to all these technologies is that we very precisely know where the vehicle is. And this is why this ego motion estimation is so important. Now, the actual strength of our radar sensors is to measure the Doppler, so the velocity. And if you're able to measure the velocity very precisely, you can very well estimate the motion of the vehicle carrying the radar sensor. And that is what I now would like to show you first. And then we go into grid mapping and synthetic aperture radar. So this here is our setup. We have a vehicle, and what we actually want to estimate is the velocity in the direction we move to, which is Vx. And sometimes we have a velocity orthogonal to it. But in any case, we have a yaw rate. The vehicle is turning. So what we need to estimate to get the motion is the velocity Vx and the yaw rate. And around the vehicle, we assume we have some stationary targets. There are always stationary targets. There are some bushes, there are some houses, fences, whatever. There are always objects, when you think about an automotive radar environment, that are stationary. Now we take the target list coming from the radar sensors, and we map all the different stationary targets into a specific diagram. And in this diagram, we have here on this axis here, the radial velocity. So the velocity that we measure with the radar sensors. And here we have the cosine of the angle where we measure the target. So the targets that are in front of the vehicle are somewhere here in this area, marked in yellow. The targets on the left side are somewhere here. And yeah, and of course, there are some which are not here on this straight line. Those targets here, these, for example, that are typically non-stationary targets. We first of all do not know which are the stationary ones and which are the non-stationary ones. So if you put everything into this diagram, a straight line appears and all the stationary targets are on this straight line. And from this straight line, you can directly estimate by very simple least square method what the yaw rate and what the Vx here, the velocity, the direction of movement is. And you can do this very precisely. Here's a measurement result. So we have a vehicle driving here, always this shape here, this rectangle. And if we have just a single sensor, we have measurement error. This is not average, or there's no tracking or anything of 0.01 meter per second. But if you use a number of sensors, so here with like 4 sensors, this value goes down. And now we have a very excellent velocity estimation and yaw rate estimation here. And that is the basis for doing grid mapping or doing synthetic aperture radar. I would like now to focus first on grid mapping, and then we go into synthetic aperture radar. Now, what is a grid map? When we have an environment, as you see it here in the picture on the right side, if we want to generate a grid map out of this environment, we first discretize this environment and we put a grid on it. Typically, the grid has maybe a resolution of, well, depending on the memory size you have, 10 centimeters if you're very good, maybe rather 15 centimeters, 20 centimeters, 30 centimeters. And it has constant grid cells. The size is constant of the single grid cells. And well, if there is a target within one grid cell, then the cell will be occupied and otherwise it will be free. And there are different types of grid maps. If you have an amplitude grid map, then you would have a high amplitude if there's an object in the grid cell. And if there's no object in the grid cell, then you would have a low amplitude. I would like to focus on occupancy grid maps. And that means we have a probabilistic grid map, which means if the probability of the existence of an object in such a cell is high, then you have a probability of 1. If you don't know anything about the grid cell, then the probability is 0.5. And if you're sure that there is no target in this grid cell, the probability will be 0. So you take the target list and you translate the target list into this global map of the environment. Of course, the radar sensor itself only does a local measurement. And this local measurement then has to be mapped onto this global map. Then you drive to another position, there you do a measurement, then you have a local map, and again, the local map is used to update the global map. And to do this update, you very precisely need to know how you moved. And this is why we need the ego motion estimation. Today we do this in a loop, and this loop is organized by a SLAM algorithm. SLAM stands for simultaneous locationing and mapping. And this is how we update this map. And here's an example. I have to start again the video. So please go to the media player. And then the video should start. Yes. So green in this map here means we don't know anything about the environment. Blue means we know there's free space. And yellow means we know there's an object. So we were driving here around a week. Oh, I have to restart it. We were driving here around a parking lot with a metallic fence. And in this video, you can clearly see the metallic fence. You can see some objects on this parking lot. And this is what a typical grid map looks like. And there where we have not driven yet, we don't know anything. So there the probability is 0.5. The question is, how does this local map look like with which we update the global map, as it is a probability map? Here is this local map. First, we need a free space model. And that basically means we have our vehicle and it has a field of view. And if there is no target in this area here, close to the vehicle in the center of the field of view, we are really sure that there is no target. So we have a very low probability of the existence of an object, which translates into this dark blue here. Out of the field of view, we don't know anything. There we have the probability of 0.5. And at the edges of the field of view, the probability increases slightly. And then we have the targets, which we put into this local map. And here you can see some targets. So they have a probability higher 0.5 because the probability of the existence of an object is pretty high there. And this depends on the signal to noise ratio, on the range, on the angle, on the Doppler, and all these informations. And then we use this local map and put it in the global map to generate this global map I have shown you before. Now, if you want to do better, if you want to get a higher resolution than what we have in those grid maps here, you can do automotive STAR, so automotive synthetic aperture radar. And here's an example. So we were driving here this path with our vehicle, doing continuous measurements. And then during driving this long straight line here, we were capturing the data and calculating SAR algorithm. In this case, it's a very simple back projection algorithm. So whenever a new sample comes, you add it to the other ones. And by that, you span a huge coherent aperture. and you get those very nice images with a very high resolution. So we get resolutions of up to 2 centimeters. So in this image, we have bird's eye, so perspective from above. We look down. So here you can see the single cars parking. There are some more cars here. This is one car here, which is somehow diagonally parked. You can even see that there is gravel here in this area, whereas here that is a normal road. And that here is a tree. The resolution is about 2 centimeters, so we can even see the single branches here of a tree. Here as well, that are the single branches of a tree you can see here. And the nice thing is there is a wooden fence on this parking lot. And typically a wooden fence is really difficult to detect in a radar image, but here you can clearly see this line here, that is the wooden fence, so it's clearly visible. So it's in the picture here, it is this fence here that you can see. And we do not see just the post, but we see the fence with the wooden board here as well. Now, let us compare this to the grid map. So here we have the grid map. When you look at the vehicles, okay, I mean, yes, if you know that these are vehicles, you can also see that in the grid map, but you would indeed need some sophisticated higher level signal processing to really confirm that these are vehicles. We cannot see that there is gravel somewhere here. There's no gravel in the grid map. The trees, okay, well, it could also be something different. There's no fence here. You can really see, what you can see is the posts of the fence. So here's one, here's one, here's one. That is something you can see. So far we were driving a straight line, but this also works if you combine it with a SLAM algorithm, if you do curved trajectories. So this here will be the full parking lot. Again, a resolution of about 2 centimeters. You can see the path where we were driving around and capturing the data. Interestingly, you can even look into the vehicles because the dynamic range of those images is that high that you can look into the vehicles. That is something I did not expect before, because I thought, okay, with an automotive radar, you could never ever look into a vehicle because the attenuation of the windscreen is that high. But yes, here's an example. All the vehicles inside look somehow like this. So this here is the back mirror and the dashboard. And here you have the front seats. Here's another front seat. So the dynamic range of those images is that high that we can even look into the vehicles and see what is in those vehicles. And just to once again emphasize how important this eco-motion estimation is, if you want to do automotive SAR or grid mapping, there's a comparison between SAR imaging, where we have used a total station to capture the ground truth position. So with a very high accuracy of about 1 millimeter, we measured where is our radar sensor with external measurement with a total meter. And this gave this image here, the above image, this one here. And then we have used the eco-motion estimation in the SLAM algorithm to do the very same imaging. And it's very difficult to see any difference between those images. If you look very, very precisely into those images, you can see slight differences here. Here is some artifact which is not in the above image. But it's very difficult to see any differences here. Now, there's one last point I would like to emphasize, and that is, if we want to do automotive SAR, we need large bandwidths. And what we have done is we have evaluated those measurements at very different bandwidths. So here is a SAR image with a bandwidth of 100 megahertz. And I have now another movie that I will start, and then we will see what happens if we increase the bandwidth from 100 megahertz to 3 gigahertz. So you need to go to the media player again. And then I start the movie, well, the animation. Okay, now it starts. 200 megahertz, 400 megahertz, 800 megahertz, 1.6 gigahertz, and 3 gigahertz. So with 3 gigahertz or 1.6 gigahertz, we get those very nice images. If we just have like 100 megahertz or even less, or 100 or 200 megahertz, you cannot see anything in those videos. Let me start it once again. I hope you can see it. So bandwidth is something really important if you do automotive SAR and want to reach resolutions being clearly better than what we can reach with the grid mapping approach. Good. With that, I'm at the end of my talk. Let me give you a short summary and a short conclusion. So I guess a future configuration of radar sensors in a vehicle, in a future vehicle, might be a high performance sensor looking to the front, because there we cannot use SAR or grid mapping in a reasonable way. And that is why we have those high performance sensors to the front. But to get the 360 degrees coverage and network of many very simple sensors, very cheap sensors, I think will do a very good job and will deliver excellent images of the environment. Of course, in the future, automotive radar will benefit a lot from 5G and 6G electronics. That is what we use already today to build digital radars. We do it in research, but of course, this hardware can be used for radar and electronics as well. And yes, there are many other topics to talk about when we talk about automotive radar. So key topics in the last few years were compressed sensing and how to apply this to automotive radar. The challenge is that we have large dynamic ranges and that we need to cover. Machine learning. At the bottom of this slide, you see an image where we do gesture recognition, so driving or traffic gestures like stopping or waving is something we try to discriminate today by machine learning techniques. Testing, target simulation, testing or test data sets, that's a very important research topic. Angular calibration is another topic, and there are many, many more. With that, I'm at the very end of my presentation. I hope you have many questions, and I would like to thank Holger Meinl and Wolfgang Menzel, that are some of the pioneers for the automotive radar, and they've helped me when doing or preparing the first part of this presentation on the more historical part of automotive radar. Thank you.
Okay, thank you, Dr. Waldschmidt. It's now time for our Q&A session. Before we start, remember that you can still submit questions through the Q&A panel. So let me take a look. So there's a question in the list, is that what's your take in applications and deployments of the millimeter wave radar, lidar, and a camera in cars? Actually, I just read an article, I believe it's in IEEE Spectrum, talk about, particular Tesla, they avoided the use of the radar. They just rely on the camera because I think it's probably cheaper in hardware. At least the cameras are cheaper. I'm not sure about the computer stuff. And the second thing, I think the second point, they mentioned that it probably requires less amount of data to be processed by the car. So yeah, so it's kind of so yeah, it will be a very interesting question. So yeah, can you provide some points on this particular question?
Sure. Thanks for this very interesting question. I'm a radar guy, so I don't know if my answer will be fair, but every few years there's another OEM, so car manufacturer, that tries to prevent using the radar because radar data is not intuitive. It's not intuitive at all. If you see what a radar measures, it measures Doppler, so velocity. That is something that is not intuitive because we as human beings don't see Dopplers. And so every few years, there's a car manufacturer that tries to not use the radar, but they all failed. Everybody is coming back to the radar and uses the radar. And today, the radar is by far the cheapest sensor that is used in the automotive sensor setup for autonomous or highly automated driving. So I guess there's no question that radar will remain one of the key sensors. It's anyway the only sensor that is really robust against harsh weather conditions. So I guess this is the radar is yeah, one of the two sensors that will always be used for autonomous driving or highly automated driving, together with video.
Thank you. Yeah, I think definitely cameras has its limitations under, for example, severe weather condition, stuff like that, or low contrast image. So there's a tech question is relatively technical. So could you please scroll back to your, I think at the very beginning regarding the hardware, there's a antenna called a reflection reduction antenna. So could you please tell us that how it works? Let me actually put this particular slide here. Yeah.
Okay, here in this yellow box, here we have this reflection reduction structure. Today, one of the key problems when you integrate a radar into a vehicle is that you integrate it behind the bumper. And the bumper is not taken into account when you do the calibration of the radar sensor. So the sensor is calibrated without bumper, and then you put a bumper above it when you integrate it. And what happens is you get multiple reflections between the bumper and the radar sensor, and this leads to angular errors, severe angular errors. And to reduce those angular errors, you need to suppress the multipath between the bumper and the PCB of the radar sensor. And this is done by this structure which reduces the reflection, at least in the monostatic direction. So what it does, it scatters the energy into all directions so that this multipath is attenuated. Basically, it's an AMC structure, and you compensate for the reflection phase of the part of the PCB where this structure is not placed. Right? So you have to analyze what is the reflection factor of the PCB, and then you place these reflection reduction structures in such a way that the reflection is reduced.
Okay, thank you. A question from Professor Gabriel Bates. So excellent talk. So his question is that if you used a simpler radar, say 3TX, 4RX, rather than using the larger element radar, would you get the same images due to the motion and the SAR?
Yes, absolutely. Those measurements you have seen there were taken with very simple radars. So we had 3 transmitters, 4 receivers. That's all. You could actually even use single channel sensors if you would find a solution for getting the ego motion. If you have a good ego motion, the imaging part can be done with a single channel sensor. Because you use the velocity of the vehicle, the movement of the vehicle.
Yep. Okay, so one more question here is that how important is the angular resolution in 2 dimensions? Is it important to have high resolution in elevation as well?
Well, I think it strongly depends on the function you want to realize with a radar sensor. If you think more about the traditional driver assistance systems, then the question is, if there's an object on the street, can you undergo or overgo this object? And this is something you have to discriminate. But when we think about highly autonomous driving or autonomous driving, then you also need in the elevation direction a very accurate angular information, because think about a parking garage where there are things coming down from above. Then you need to very precisely know where's the free space where I can go to with my vehicle. And that always means you need elevation information as well.
Okay, thank you. A question regarding actually the data processing. So most of the operations have to be performed in real time. What about the time of computation of the process used?
I think concerning all the topics I've shown here, of course, automotive SAR, so synthetic aperture radar, is the one which needs most computational power. But in the last 2 years, we have seen a number of publications where people have shown that you can do this in real time as well. So it is feasible doing this in real time. But of course, we are talking about, yes, you need to parallelize it and so on. So it's a large computational effort. Yeah, no question.
Mm-hmm. And let me see. Certainly, there are a lot of questions. I mean, in the system, we will not be able to answer all the questions, but we will be able to forward those questions to the speaker so that the speaker can follow up with you later by email. But before we conclude, let me take one more question. So a question is that does multi-beam antenna has applications in automotive radar?
Multi-beam antennas?
Mm-hmm.
Well, in the past, we have seen many automotive radars which use some type of scanning antennas or classical phased arrays. Today, actually, all sensors are using the MIMO principle. And as we have shown, there is no contradiction between doing MIMO and transmit beamforming or beamforming at the very same time. If you do MIMO, you do beamforming, digital beamforming on the receive side anyway. So I would say for future radars, I wouldn't expect any multi-beam configurations in the sense of analog multi-beam systems, but of course in the digital signal processing, we have different angular regions where we do different types of angle estimation.
I guess the multi-beam antenna, if you know, I think it probably will cause a lot of. So you don't know where the signal is actually coming from, right? If you have multiple beams simultaneously, if you're not able to, differentiate the signals from the different beam, is that what you? That's what I understand, right?
Yes. If you would have a traditional multi-beam system, you wouldn't need to make sure that you know which beam and which direction a signal comes from. If you have a MIMO system, you anyway do the angle estimation in the digital process, and there you get also an array gain, and you wouldn't fight with the problem anymore that you don't know which signal comes from where, and you have different signals and so on.
Okay. All right, last question. So this question is not technical. Okay, so in your opinion, which automotive company is ahead in terms of automotive radars?
I don't know. I don't know. It's really difficult to say because, well, whenever there are new vehicles coming, it is quite impressive what new functions are there. But it's still a long way until we have highly automated driving or autonomous driving within the cities. I mean, of course, you can do a system, you can use a system that is maybe made more for non-city environments, also within a city, but there, everybody who does this knows this quickly that the system is still very limited. So I think until we have fully autonomous driving within cities in a really robust and reliable way will still take some time.
Okay, thank you so much. I really wish that maybe after another 20 or 30 years, then we will talk about the fully autonomous driving cars with high safety, right? That will be really good, for the our generation. I think that hopefully that will be. We'll see. Hopefully that technology always grows in an unexpected rate, which beyond our imagination. So, but thank you everybody. So we're running out of time. So again, as I said, the presenter can follow up, on the unanswered question. And this session will be archived on the society website at mtt.org, and all registrants will get an email reminder with a website address when it's available. And if you are interested in receiving a PDH credits, which let me show you right here. So if you are interested in receive this certificate, please follow the link and write down the code to receive your certificate. And a special thanks for our audience for joining us today. We hope you find today's event valuable and that you will return for future IEEE MTT Society webcast, as typically on the second Tuesday of every month. And it's at noon Eastern Standard Time. Thank you so much and have a good day.
Thank you very much. Goodbye.
You can stay.
I stay.